In this video, I want to show you how to evaluate a few of the more complicated inverse trig expressions. This is a very, very common problem that we're asked to do quite often. What they'll do is they'll stack a regular trig function and an inverse trig function. So if you recall, what happens with these inverse trig functions is the output of an inverse trig function is an angle, and so whenever you get that output, you're going to turn right back around and plug it in a trig function and get a final value. So that's why they're usually stacked as these layers here. So I'm just going to work through a couple of examples here. All right, so first up is sine of secant inverse of 2. It's a very weird quantity. So what we do, the way we start these for all of these type of problems, is we ignore the outside and we're just going to look at the inside because we have to evaluate that before we can take sine of it. So what I'm going to do, I'll color code these. I'll do this part in green. I'll take secant inverse of 2 and try to evaluate that off on the side. So like you, we're not that comfortable dealing with inverse trig functions, at least as much as we are regular trig functions. So I'm going to use the trick I used in the last video. I'll set this equal to y or x or k, or pick a letter, and then I'll take secant of both sides, and this will yield the relationship secant of y equals 2, right? Secant of y on the left, secant of secant inverse cancels on the right, and you're just left with 2. And so this is a little bit more comfortable because we don't have inverse functions anymore. So secant of y equals 2, even that's a little strange because we would much prefer dealing with sine and cosine as opposed to secant. But if you recall, secant was the same thing as 1 over cosine, 1 over cosine. So we can write this as 1 over cosine of y equals 2. Or we could rewrite that as cosine of y equals a half. Perfect. That seems very reasonable. So what we're really looking for is an angle so that if we took cosine of it, we would get a half. So look on your unit circle, cosine of which angles would give you a half. Well, let's see here. I think this angle here at pi over 3, I know cosine of pi over 3 is a half, as well as this angle. This will be 5 pi over 3. This is not our guy though, because again, I'm not going to go into a lot of detail about this, but there was that issue of restricted domains and whatnot when we were first learning about inverse trig functions. So I know that this is the only interval from 0 to pi, which is cosine's restricted domain, and so that'll be the restricted range of the inverse cosine function, in this case inverse secant function or whatnot. So I want pi over 3 as my y value. And so y, if I'm going to squeeze this in here, y, cosine of y equals a half. Y is pi over 3. But check it out. This was also secant inverse of 2. That's what we called secant inverse of 2 temporarily. We called it y. So this part on the inside here that I'm highlighting in yellow, that is pi over 3. That's the secant inverse of 2 that we found on scratch paper. All right, so now in yellow, all I really have to do is take sine, not of this weird secant inverse of 2 or what have you. It's really just sine of pi over 3. That's really all it is. And sine of pi over 3, as we all know, is root 3 over 2. So that would be your final answer. So these are done in layers. You do the inside layer first with the inverse trig expression or whatnot. Find out what angle that represents, in our case pi over 3, and then you apply the trig function, the regular trig function on the outside, to that angle, whatever that angle may be. In this case it was root 3 over 2. Okay. We also threw in a little twist that we haven't seen before with this example with the secant as well. Mostly in the last video we dealt with just inverse sine and cosine. All right, let's try another one. Let's see if this next one makes sense here. All right, these are another very common type of example. They initially look the exact same as the first type, but there's a twist. So I see the 2 layers here, so I know right off the bat how I'm going to set it up. I'm going to take this guy on the inside. I'm going to start with him. I'll call him y. So I'm really just taking tan of y, but I have to figure out what y is. So if we set up an equality, y equals arc cosine of 3/5. Oops, if I can write it correctly, of 3/5. I'll take cosine of both sides so that my equation has regular trig functions as opposed to these weird new inverse trig functions. So I have this relationship, but then I get stuck at a weird place. You start thinking cosine of what angle would give you 3/5? That's pretty strange, isn't it? I don't know. 3/5 isn't a nice unit circle value. If you think about your unit circle, I'm sure there is an angle whose x coordinate is 3/5 or 0.6, but I have no idea who he is. That's not a standard angle. Well, here's what we do for these examples. This is a very, very common thing that's done quite often. This actually relates back to right triangles. You probably remember right triangles from some time ago. Here's what happens with these guys. If you consider a right triangle, sorry, I know that's not the best, but if you consider a right triangle, what we've got going on here, excuse me, is we're taking cosine of some angle, and it's giving you the ratio 3/5. Think way back to your pre-cal days. Do you remember like SOHCAHTOA, or sine is opposite over hypotenuse? And here, let me jot it down. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So we have these three trig relationships. That's where sine and cosine and tangent came from. Well, that's precisely what's going on here. Y is your angle, cosine of y, and that'll be the ratio adjacent side of 3 and hypotenuse of 5. So in this right triangle, cosine of y is in fact 3/5, adjacent over hypotenuse. So if here's y, and then this will set a particular right triangle, what I actually want is tangent of that angle. So let me think for a minute. What is tan of y? What is tangent of this angle here? Well, it's opposite over adjacent. Opposite over adjacent. The only problem with this, the only reason I'm not able to finish this right off the bat, is I don't know what the opposite edge is. I know the adjacent and I know the hypotenuse. But then you think about it for a second and you say, oh, wait a minute. I know the Pythagorean theorem. A squared plus b squared equals c squared, right? So I think we all know that. A squared plus b squared equals c squared. So if I jot that down up here in the corner real quick, 3 squared plus, I'll call it a squared equals 5 squared. I'm not going to go through the algebra. I think we all know that a is 4. 3 squared plus 4 squared equals 5 squared. So this side here will be 4, and I have my answer. Tangent of y is 4/3. So when you see weird numbers like 3/5 and things that clearly aren't in the unit circle, just realize you're going to be using a right triangle that has usually nice integer values on its sides. And so you make your right triangle up, you find your angle in that right triangle, and then you're just taking tangent, in this case, of that particular angle. All right, now these are all very common, so I can actually go ahead and tell you which ones you'll see, and you can open up your textbook and you verify these. Any of these that have these double sines with an arc secant, or tangent with an arc cosine, or whatever the case may be, that use right triangles, almost exclusively you'll see these numbers. These will be the numbers that you see for these problems. You'll see 3s and 4s and 5s, because this is a 3, 4, 5 right triangle. You'll see right triangles with 5, 12, and 13, because 5 squared plus 12 squared equals 13 squared, and 8 and 15 and 17. These are probably the three most common right triangles that are used. And so I would encourage you, open up your textbook and notice how often these numbers are used. So just be aware of that, when you're doing some of these problems, and you almost surely see these show up on a test. So that's how we evaluate some of the more difficult inverse trig expressions. So hopefully that makes a little bit more sense. Dealing with inverse trig expressions or functions, we still have to talk about some of the calculus topics. So now you can move on to watch those videos now.